This is an empirical study based on selected EV and EV charger models available in New Zealand. Here's a quick overview of my presentation. So these are the headings. I'll be going through each and every topic in detail during my presentation. Right, so first of all, before moving forward, let me briefly introduce the setting. So as we all know, in 2015, the Paris Agreement has mandated a rapid and deep decarbonization of all economic sectors, including transport. This is to limit the global temperature rise in this century under 1.5 degrees Celsius above pre-industrial levels. Along this line of decarbonization, Aotearoa New Zealand has committed to be part of this global effort by reducing transport-based emissions by 41% at the end of 2035. This is to reach the long-term goal of net zero by 2050. The government also sets an aspirational target of reaching 100% renewable electricity by 2030. So, to promote this decarbonization concept, government has recommended phasing out imports of all fossil fuel cars by 2035, then to reach and to promote the adoption of electric vehicles. At present, there are more than 106,000 EVs available in New Zealand, out of which more than 74,000 are pure battery electric vehicles, whereas more than 32,000 are plug-in hybrid vehicles. If you look at this bar chart on the top, get my laser pointer. So this shows how the EV numbers have increased over the years. So there's a rapid growth in EV numbers in New Zealand. And according to this S-curve, which is published by the Ministry of Transport in New Zealand, it is expected to reach 100% new EV registrations by 2030. So the current trend is somewhere here, but by 2030, we are expecting to reach all new EV registrations. This rapid growth in EV numbers can only be sustained if we have accessible and affordable charging infrastructure, which means we need more charging stations. We need more DC fast charging stations as well as AC home chargers. Given the necessity and popularity of EVs and EV chargers within New Zealand infrastructure, our project investigated these objectives. I'll be talking about the first 4 objectives today, but we have also done 2 secondary work on these topics as well. So the first objective was to evaluate efficiencies of 8 typical EV chargers in New Zealand. Out of those chargers, we tested 4 were DC fast charging stations and 4 were AC fast charging stations. We also looked at various active thermal management systems used by 4 common EVs in New Zealand. So we studied the battery heating mechanisms, battery cooling mechanisms to determine the internal charge efficiencies of these 4 EV models. I'll mention the EV models and the EV chargers in my next slide. So knowing the EVSE efficiency, which is the charge efficiency, and also knowing the EV internal efficiency, which is the efficiency of the onboard charger, we combine those 2 efficiencies to determine the overall grid to battery efficiencies for certain EV-EVSE combinations. As I indicated earlier, we have also done research work on OCPP compliance testing, that is to see how these EV chargers respond to demand management. So this part I'm not talking today, but we have studied that as well. Also, we looked into various harmonics aspects of these EV chargers, especially looking at the total harmonic distortions of voltage waveforms and current waveforms. We found how these EV chargers going to affect the power quality. So here are some photos we took during the charging cycle. So the one at the bottom, the first one is a Tesla Model 3 under charge. The second one is the Hyundai Ioniq when it's connected to the charger, and the third one is the BMW i3 when it's connected to the tritium charger, and the fourth one is the photo of the fast charging station, which is the 60 kilowatt Fihong charger. So our research focused on testing these 8 EV chargers. So I'll start with the first one. Under AC chargers, the first one, which is the EVSE 1, is the 7.4 kilowatts Siemens charger, and EVSE 2 is the 22 kilowatt three-phase Etrel charger. EVSE 3 is New Zealand-made 7.4 kilowatt single-phase EVNEX charger, whereas EVSE 4 is the single-phase ABB charger. Out of the 4 DC fast charging stations we tested, the first one, EVSE 5, is the 25 kilowatt Delta charger, and EVSE 6 is the 30 kilowatt Fihong charger, and EVSE 7 is the 60 kilowatt Fihong fast charging station, and also EVSE 8 is the Australian-made 50 kilowatt tritium V-fill charger. So these chargers were the test units under our study. So while testing these chargers, we have connected these 4 EV models as our load devices. EV1 is the Tesla Model 3, and EVSE 2 is the BMW i3 model, and EV3 is the Hyundai Ioniq 3, which is a sedan car, and EV4 is the 2017 Nissan Leaf with a 24 kilowatt hour battery pack. So these 4 EVs, they had various charging protocols. As we know, their charging connectors are different. So if you look at these 2 charging configurations, CCS and CharDemo, CCS stands for Combined Charging System, and it's widely used by American and European automobiles. So here in this diagram, you can see CCS1 and CCS2 connector types. Whereas the other charging protocol, which is the CharDemo protocol, CharDemo means charge for moving. It is widely adopted by Japanese automobiles, and here the image of the CharDemo connector can be seen. Right. Now, to talk a bit about our testing methodology, we have monitored input power as well as output power for various EV chargers under our study. We also considered the resistive losses in charging cables. To monitor the power measurements, we used Hioki power analyzers, which is Hioki PQ3198 model, the newest version, and the Hioki PW3198 version as well. So power in and power out readings were recorded at 1 second intervals throughout the charging cycles. Also, we maintained an accurate synchronization between the input and output power signals. If you look at this diagram here, DC charge point configuration diagram, it shows that we measured the 3-phase input power to the fast charger, and we measured the DC output power as well. In the AC charge point configuration, for a single phase scenario, we've measured the single phase power in and single phase power out. For all these EVSE charge profiles, we used EVs as the load. Each electric vehicle was charged for at least 3 times against each EVSE under testing. So if you look at the total number of charging cycles, 8 EV chargers and into 4 different EV models, and each model 4 times. So we have, I think, repeated more than 100 cycles of charging during our study. So for these charge profiles, the initial conditions were a fully discharged EV battery as permitted by the battery management system, because some EVs will not allow the full discharge up to 0 SOC. In most cases, we saw like at about 4% SOC, the car goes to a idle kind of a turtle mode. And the end, yes, the end of our charging, we carried out our charging cycle until the EV battery was fully charged. And in some cases, we saw the 100% SOC mark cannot be achieved because BMS stops the car charging procedure to prevent any excessive battery heating. Based on the input and output power measurements, and also considering resistive losses associated with charging cables, we adopted a simple method to evaluate the efficiencies as below. When the power was monitored close to the AC mains end, we have subtracted the power loss in the input cable. And when the output power was recorded close to the EV end, we have added that extra loss in the cable. So knowing P out and P in values, we simply determine the efficiencies. And this diagram here shows our efficiency results, and these are all average results. I have another slide to show you how the efficiency profiles vary during the charge cycle. So in this one, the blue color bubbles all indicate AC charger efficiencies, whereas the black bubbles indicate DC fast charger efficiencies. So it is clear that AC chargers perform exceptionally with efficiencies over 99%. This is because these AC chargers, they won't perform any power conversion. They simply allow the mains power to flow into the car based on a relay switching mechanism. But in the cases of DC fast chargers, we saw varying results, especially EVSE 8, the 50 kilowatt charger, revealed a low 91.68% average efficiency compared to its rated efficiency of 94%. So this is a substantial reduction, and this significant reduction is due to various energy losses. Energy losses such as heat losses, inductive losses, because some of the chargers had massive inductors inside, and standby power consumptions, and also at the end of the charging cycle, these cooling mechanisms trigger to cool down the charger. So all the power wasted on these various ways reduce their efficiencies. The two best performing DC chargers were EVSE 5, the 25 kilowatt charger, and EVSE 7, that is the 60 kilowatt charger. So they both revealed efficiencies above 94%. So in the last slide, I have presented the averaged efficiencies, but efficiency itself is a function of the charging cycle. So these three plots here show the efficiency profiles of different fast chargers we tested. So according to these three figures, we can see when the operating power of the EV charger is close to its max rated power, the efficiency becomes very high. But if it is under 25% of its rated power, the efficiency tends to drop remarkably. So these diagrams show, especially below 10 kilowatts of power, for a massive charger, for a 60 kilowatt charger, efficiency drops significantly. So our next aim was to study the internal energy consumptions within the cars. So when studying these internal energy consumption patterns, it is essential to consider various active thermal management systems used by different car manufacturers. These active thermal management systems are controlled by the battery management system to prevent any excessive heating. Also, it is indicated by the manufacturer that the optimum temperature range for EV batteries is around 25 to 40 degrees Celsius, as a cold battery can reduce the range up to 30%. Also, under charging and also under driving, if the EV battery gets too hot, it can have an adverse effect on the longevity of the battery cells. Therefore, controlling the temperature and maintaining this ideal battery temperature is important. So various preconditioning techniques are activated by the battery management system to heat and cool down the battery packs. So here on this table, we can see the 4 EVs we tested had different mechanisms for cooling and heating. If you look at EV1, which is the Tesla Model 3, it is mentioned that the car inefficiently functions the motor to generate heat to warm up the battery. Whereas in the case of EV2, that is the BMW i3, a resistive heating mechanism is used to heat up the battery. EV3, the Ioniq sedan version, uses resistive heaters or heat pumps depending on the country of manufacture. Also, EV4, which is the Leaf one, it uses heat pumps and hybrid heating system to heat up the batteries. This bottom row shows various cooling mechanisms used by these cars. Tesla 3 EV1 uses liquid cooling or glycol cooling for to cool down the battery pack when it's too hot. Whereas BMW i3, which is EV2, it uses air cooling, aluminum tubes with cold air flow to cool down the battery. EV3, the Ioniq 3, it uses air cooling using a fan. And interestingly, Nissan Leaf, it has no active cooling mechanisms. It simply throttle the charging speed to reduce the heat buildup of the EV battery. So based on the benefits of these active thermal management systems, we think that this energy consumption by the car for heating and cooling is not a waste. Instead, it gives its own benefits. However, during our efficiency calculations, we have taken into account these energies associated with cooling and heating. Based on the hierarchy power measurements, for each EV model against each EVSE, we determine the maximum charging power observed by different AC and DC chargers. We know under DC charging, the charger power that is supplied to the car is used for charging the battery, which is battery power, and the thermal management power, and also the power lost in cables, as well as the power consumed by the EV internal circuits. However, in the case of AC charging, the charger power that is supplied to the car is used for battery charging, and also there's a conversion loss inside the onboard charger of the car. So here, PAC to DC signifies that power conversion loss which is inside the car, and also thermal management power and cable power and EV internal circuit power as in the case of the DC charging. So this diagram here, the bottom diagram shows that in AC charging situations, the AC power that is inputted to the EV onboard charger is converted to DC power, and part of that DC power is used for battery charging, and the rest of that power is allocated for battery heating and battery cooling as triggered by the active thermal management system of the car. This table shows some interesting results. The three-phase 22 kilowatt AC charger, if you can see this green row here, it delivers only about 50% of its rated power or below for all the cars we tested. And we believe this charger rated power reduction is mainly due to the EV onboard charger reaching its charger limitations. And also we believe battery management system inside the car sort of controls that input power to prevent any excessive heating. Interestingly, the 60 kilowatt DC charger, which is the Fihong 60 kilowatt charger, delivers only about 73% to 80% of its rated power to the car for all the combinations that we tested. This substantial underrated power of this 60 kilowatt DC charger, we believe, is due to the EV charger reaching its maximum current output limit before it reaches its maximum power output limit. Compared to a 400 volt battery pack, which limits this charger power intake, we believe a 800 volt battery pack will allow the full 60 kilowatt of power to be consumed by the charger. Next, I'll show a bit of details about our experimental methodology. So when determining the internal charging efficiency, we wanted to monitor the power input to the car as well as the power consumed by the EV battery pack. To record power input to the car, we use hierarchy power analyzers, whereas to record the battery power, which is inside the EV, that was recorded using the OBD2 Bluetooth scanner. So we have connected OBD2 Bluetooth scanners, and then we connected that to our computers and recorded the battery power results under charging. So this diagram here illustrates the BMS data logging system using OBD2 scanner when we performed AC charging as well as DC charging. Knowing charger power and battery power, we can monitor the internal efficiencies. So here, these waveforms show both charger power, that is in blue color traces, and the battery power, that is in red color traces. So these were recorded for both AC and DC EV chargers at every 1 second intervals. The middle figure, which is figure B, shows that the EV1, which is the Tesla Model 3, when connected to EV6, which is the 30 kilowatt DC charger, it consumes almost 50% of its initial charge power to heat up the battery or for active thermal management. That's why this battery power curve drops during that initial charging time. Interestingly, this figure shows the highest allocated heating power out of all the combinations we tested. The other two figures, figure A and figure C, they have similar charging behaviors. Both EV1 and EV2, when connected to EVSE 4, shows that out of the 7 kilowatts or 7.2 kilowatts of power that is given to the car, almost about 6.5 kilowatts is utilized for battery charging, which means the heating power or the thermal management power consumed for those two AC charging situations are very less. So these three figures also indicate different charge profiles that we have obtained during our testing. EV2 and EV3, when connected to EVSE 5, that is the 25 kilowatt Delta charger, they both had remarkable similarity in their charging patterns. We see that this gap between the blue color trace and the red color trace is very minimum. Maybe a maximum of about 1 to 2 kilowatts is used for battery thermal management, whereas the majority of the power is allocated for battery charging. That's why the gap is very minimum between these two traces. Figure E, the middle figure, also shows a similar pattern to the one that we saw before. EV3, when connected to EVSE3, so which means EV3 is Hyundai Ioniq, and EVSE3 means the Evonex 7.4 kilowatt charger. So in this AC case, out of 7 kilowatts, almost about 6.5 kilowatts is used for battery charging. So right. Knowing the charger power and battery power measurements recorded for various measurements, we determine the internal efficiencies as below. So internal efficiency is given by E battery over E charger times 100, where E battery is the cumulative energy input, E charger is the cumulative energy input to the EV as derived from the AC-DC output power measurements, whereas E battery is the cumulative energy absorbed by the car battery as recorded by the onboard BMS data records via the OBD2 connection port. So the internal charge efficiencies for the three EVs we tested vary like this. Under AC charging, all EV models performed consistently with internal charging efficiencies varying between 91% in the case of EV2 to 92.7% in the case of EV1. So this under DC fast charging, we saw that EV1 Tesla Model 3 demonstrated a substantially lower efficiency of 90.6%. So we believe the advanced thermal management systems of the Tesla Model 3 consumes a significant power share for battery heating, and that's why the internal charge efficiency of EV1 under DC charging dropped to 90%. On the other hand, EV2 and EV2 were efficient under DC charging with internal efficiencies over 97% and 98% respectively. Averaged results, if you look at this last column, under AC charging, the averaged internal efficiency was 91%, whereas under DC cases, it was about 95%. So we believe that average efficiency under AC charging dropped because of that internal power loss, that is the AC to DC conversion loss that happens inside the EV onboard charger. Right. So far we have talked about two different types of efficiencies and presented results according to that. So first one was the EV charge efficiency, and the second one was the EV internal efficiency. So combining the two together, EVSE efficiency and the EV internal efficiency, we determine the overall grid to battery efficiency according to this formula. In the case of AC charging, the grid power that is supplied to the AC charger is then supplied to the EV, where the EV onboard charger converts that AC power into DC power and allocate that power to thermal management as well as to battery charging. In the case of DC charging, the grid power is converted within the DC charger and it outputs DC power, and that is simply allocated to battery as well as the active thermal management system inside the car. So this table here summarizes all our efficiency results for the total grid to battery efficiency scenario. Though those AC chargers performed exceptionally with 99% efficiencies, but when that efficiency is combined with the EV internal efficiency, overall grid to battery efficiency drops. As we can see, the best averaged efficiency under AC charging was recorded by EV1 with about 92.6%. Interestingly, the same car showed a huge drop of efficiency when it comes to the DC charging situation, where the DC combined grid to battery efficiency dropped to about 85%. The same Tesla Model 3 has contrasting results under AC charging and DC charging. EV2 and EV3, they demonstrated similar charging trends with grid to battery efficiency varying between 90.4% to 91.7%. So we believe both EV2 and EV3, which is the BMW i3 and the Ioniq 3, they have similar thermal management systems inside the car, and that they are more efficient under DC fast charging than the case of AC charging. Notably, the averaged grid to battery efficiency of all EV chargers that we tested varied between 90% to 91%, except for the special case of EVSE 8, which revealed a significantly lower efficiency, grid to battery efficiency of 87.2. So this EVSE 8, which is the 50 kilowatt tritium charger, and interestingly, it is the most abandoned EV charger in New Zealand with more than 300 units currently installed everywhere in New Zealand. So based on our findings and the manufacturer recommendations, ECA, that is the Energy Efficiency and Conservation Authority in New Zealand, they have published a list of EV chargers as their approved list. So this selection was based on two factors according to their website. So the link here, you can see here, that link shows that approved list. So the two factors they considered, number one was the efficiency. So with very much less energy losses, efficiency was a critical factor. And also they considered the smartness of the EV chargers. So they recommended EV chargers which support the demand response management, as well as the ones which are capable of two-way communications, which means, like the charging case of grid to battery, these chargers must be able to support vehicle to grid as well. So the one that we tested, Aotearoa charger, is included on that list here. It is interesting to see that the only DC charger they have recommended was this red face 200 kilowatt charger, which is a New Zealand made ultra fast charger made in Napier, Hastings. Right, so I would like to make some conclusions and future thoughts based on our findings. We saw that large power savings can be made nationally if the EV charge efficiency can be maximized. Even 1% loss of efficiency is significant, considering the magnitude of power these chargers handle and also the number of EV chargers currently available. We believe if we can shave even 1% of efficiency, it's going to be a significant factor for our growing EV fleet in New Zealand. Also, it is important to select the correct EV to the correct EVSE when it comes to charging, because we saw not all electric vehicles are ready to accept the maximum power delivered by the charger. We saw various controls such as the battery voltage, BMS system, and onboard charger limitations. All these factors control the power input to the car. So it's very important to get that right combination when it comes to a charging cycle. Otherwise, we'll be paying more for the charging stations. Also, we saw active thermal management of the EV batteries very critical to maintain the optimum range and the longevity of the battery packs. So it is mentioned that a temperature of about 25 to 40 degrees is the ideal battery temperature. And according to the discussion before, we believe this internal energy consumed on battery thermal management is not a waste. It's a useful thing. And we also saw the combined grid to battery efficiency varies between 85% to 92.6%. So considering these situations, we saw more modern EVs, such as the Tesla Model 3 and other new cars, having advanced active thermal management systems. They provide shorter charge times. However, they also utilize large levels of power for battery thermal management. And the question we have is the costs and benefits to the consumer as well as to our environment with these intensive thermal management strategies. So this would help us to predict our future national power demands as we step towards a net zero future. Thank you very much for listening to my presentation.